There is a harbor wall sitting at the bottom of the Mediterranean Sea that has been hardening for 2,000 years, and it is stronger today than the day it was built. The material that built it required no kiln, no factory, and no fossil fuels. And the reason every modern engineer knows this and still pours Portland cement anyway is not a mystery. It is a decision. There is a structure submerged beneath the waters of the Mediterranean Sea right now that has been getting stronger every single year for 2,000 years. Not holding, not surviving, getting stronger. The mineral crystals binding its internal structure have been growing continuously since the moment Roman laborers packed the last stone into place and walked away. Modern concrete, the material holding together every bridge, dam, tunnel, highway, and apartment tower built in the last 150 years, begins to degrade the moment it is poured. Within 50 years, most of it is cracking. Within a century, significant portions of it are failing. The Roman structure on the seafloor is not cracking. It is not failing. It is, by every measurable standard, improving. And the reason that matters is not archaeological. It is financial. It is environmental. And it is a direct consequence of a decision that the global construction industry made in the 19th century and has never revisited. To understand what Roman concrete actually is and why it behaves so differently from the material holding up the building you're sitting in right now, you have to go back to a place in Italy called Pozzuoli. Pozzuoli sits on the edge of the Campi Flegrei volcanic field, a sprawling underground system of supervolcanic activity that has been venting heat and ash into the surrounding landscape for hundreds of thousands of years. The soil around Pozzuoli is dark and fine and strange. Farmers working that land 2,000 years ago noticed that it behaved differently from ordinary soil. Mixed with water and lime, it hardened. It hardened underwater. It hardened in conditions where ordinary lime mortar simply dissolved and washed away. The Romans called this material pozzolana, named after the town itself. They did not fully understand the chemistry behind it. They did not need to. What they understood was that it worked, and they built an empire with it. The Pantheon in Rome, which has stood without structural intervention for nearly 2,000 years, was built with a variation of this material. The Colosseum, which absorbed the impact of earthquakes and centuries of stone quarrying by medieval builders, stripping it for parts, and still stands, was built with it. The harbor at Caesarea Maritima, constructed by Herod the Great using Roman engineering, was submerged in the Mediterranean for 2,000 years, and when marine geologists examined its core structure in the early 21st century, they found something that stopped the research team cold. The concrete was not just intact. It was threaded through with a mineral called tobermorite, a rare crystalline structure that forms only under specific chemical conditions, growing inside the concrete matrix like a slow and silent reinforcement system, filling microscopic gaps, binding aggregate to paste, strengthening the material from within. Tobermorite does not form in Portland cement concrete under any ordinary conditions. It formed in Roman concrete because of a specific chemical reaction between the volcanic ash, the seawater, and the lime. A reaction that took decades to complete. A reaction that modern concrete cannot replicate because modern concrete does not contain volcanic ash and is not designed to take decades to reach its final state. It is designed to reach its final state in 28 days and then hold, and then slowly, inevitably begin to fail. Marie Jackson is a geologist at the University of California who spent years studying Roman marine concrete. When her team published their findings in the journal American Mineralogist in 2017, the paper described in precise technical detail exactly how the reaction worked. Seawater, percolating through the Roman concrete, dissolved the volcanic ash at a molecular level. The dissolved components then reacted with the lime in the mixture to produce new minerals inside the structure. The concrete was not a static material sitting inert inside harbor wall. It was an ongoing chemical system, slowly and continuously building new mineral architecture inside itself. Jackson described it as a living material. That description is not metaphorical. The mineral growth inside Roman marine concrete is measurable, documentable, and ongoing after 2,000 years of continuous submersion in seawater. The question her team was not asked to answer, but that the data raises is a simple one. If we have known since at least the early 20th century that Roman concrete contained volcanic ash, and if the structural performance of Roman concrete is observable and documented, and in many cases literally standing in the middle of major European cities, why does the modern construction industry not use volcanic ash in its concrete formulations? The answer requires understanding what Portland cement is, where it came from, and what interests it serves. Portland cement was patented in England in 1824 by a bricklayer named Joseph Aspdin. The name was a marketing decision. Aspdin thought the hardened cement resembled the limestone quarried on the Isle of Portland off the southern English coast, and he named it accordingly. The manufacturing process Aspdin developed involved heating limestone to extremely high temperatures in a rotating kiln, driving off carbon dioxide, and producing a highly reactive powder that, when mixed with water, hardened rapidly and predictably. Within decades, Portland cement had become the dominant building material of the industrializing world. The reasons were straightforward. It was fast. It was consistent. It could be manufactured at industrial scale from limestone, which exists in enormous quantities on every continent. It set in 28 days regardless of weather, temperature, or the skill of the laborers using it. It was, from a manufacturing and logistics standpoint, nearly perfect. What was not was chemically sophisticated. Portland cement concrete works through a process called hydration. Water reacts with the cement powder and produces a calcium silicate hydrate gel that binds aggregate together as it hardens. The process is fast and the initial product is strong. But the calcium silicate hydrate gel is not a stable long-term structure. It is vulnerable to chloride ion penetration, which corrodes the steel reinforcement embedded in virtually all modern concrete construction. It is vulnerable to a process called alkali-silica reaction, in which certain aggregates react slowly with the alkaline cement paste and produce a gel that expands and cracks the concrete from within over decades. It is vulnerable to freeze-thaw cycling in cold climates, where water penetrates microscopic pores, freezes, expands, and progressively fractures the internal structure. The Roman concrete sitting on the floor of the Mediterranean has been continuously exposed to seawater for 2,000 years and is not cracking. The reinforced Portland cement concrete bridge built in 1972 has spalling concrete and exposed corroding steel and is scheduled for replacement. The contrast is not subtle. The carbon cost of this choice is not subtle either. Producing 1 ton of Portland cement clinker, the reactive powder at the heart of modern concrete, releases approximately 900 kilograms of carbon dioxide into the atmosphere. The world produces approximately 4 billion tons of cement every year. The mathematics produce a number that accounts for roughly 8% of all global carbon dioxide emissions, more than the entire aviation industry, more than all maritime shipping. And unlike those industries, cement has no obvious clean alternative within its current chemical framework, because the carbon dioxide released in cement production comes not just from burning fossil fuels to heat the kilns, which could theoretically be replaced with cleaner energy sources, but from the limestone itself. When you heat calcium carbonate to 1450 degrees Celsius, it chemically decomposes into calcium oxide and carbon dioxide. The carbon is in the rock. You cannot heat the rock without releasing it. There is no version of Portland cement production that does not emit enormous quantities of carbon dioxide, regardless of what energy source powers the kiln. Volcanic ash does not have this problem. It does not require a kiln. It does not require temperatures above room temperature. It does not decompose into carbon dioxide when mixed with water and lime. It is, in the most literal sense, a material that already exists, already distributed across volcanic regions, covering a significant fraction of the Earth's land surface, already proven over 2,000 years of continuous structural performance, and requiring only lime and water to activate. And in 2014, a research team at the Massachusetts Institute of Technology published a paper demonstrating that Roman-style volcanic ash concrete could be reproduced in a laboratory. The material they produced matched the performance characteristics of ancient Roman concrete. The tobermorite formation was observed. The long-term strengthening mechanism was confirmed. The paper did not suggest that this material could replace Portland cement in all applications. Skyscraper cores and major bridge decks still require the compressive strength that modern high-performance concrete can achieve. But for harbor construction, seawall reinforcement, coastal infrastructure, foundation work, and the enormous volume of global concrete production that does not require maximum structural performance, volcanic ash concrete is not a theoretical alternative. It is a documented, reproducible, high-performance material that gets stronger over time instead of weaker, emits a fraction of the carbon dioxide of Portland cement production, and has been proven at the largest possible scale by the most demanding possible test. 2,000 years of continuous exposure to the ocean. The barriers between this material and widespread adoption are not scientific. The science is settled. The barriers are economic and regulatory. Portland cement is embedded in every building code, every structural specification, every insurance framework, and every supply chain in the global construction industry. Switching to a different binding material requires new testing standards, new performance specifications, new insurance categories, and new supply chains for volcanic ash, which, while abundant, is not currently distributed through the logistics networks that deliver Portland cement to construction sites on every continent. These are real obstacles. They are not insurmountable. They are the ordinary friction of a large industry being asked to change a material it has used for 150 years. The testing is happening. Research groups at the University of California, at the Massachusetts Institute of Technology, at universities across Europe and Japan are generating the performance data that standard-setting bodies require. The timeline is measured in decades, not years. But the direction is not in question. What is already happening today is worth paying attention to. Volcanic ash deposits exist in Italy, Iceland, the Western United States, Japan, Indonesia, the Philippines, Central America, and across the East African Rift System. Several companies in Iceland, where geothermal volcanic activity makes ash readily available, are already producing low-carbon cement blends incorporating volcanic material. Roman-style concrete formulations are being tested in marine construction projects in Europe. The United States Army Corps of Engineers has funded research into natural pozzolan concrete for use in infrastructure projects where long-term durability under harsh environmental conditions is the primary requirement. The knowledge exists. The material exists. The performance record exists. What exists between this material and the construction site down the street is not a scientific gap. It is a gap between what we know and what we are willing to change. The Roman engineers who built the harbor at Caesarea Maritima, who mixed volcanic ash with lime and seawater and packed it into wooden forms and submerged it in the Mediterranean, did not know they were building something that would still be getting stronger 2,000 years later. They did not have the tools to measure tobermorite crystal growth. They did not have the vocabulary to describe alkali-silica reactions or chloride ion penetration. What they had was observation. They had watched this material perform. They had seen harbors built by previous generations still standing. They trusted the material because the material had earned that trust across generations of demonstrated performance. We have the same information they had, plus 2,000 years of their construction record to study, plus the molecular analysis, plus the laboratory reproductions, plus the carbon accounting. And we are still pouring Portland cement. The question is not whether volcanic ash concrete works. It has been working continuously since before the first Roman emperor took power. The question is how long it takes an industry producing 4 billion tons of material every year to look at a harbor wall on the floor of the Mediterranean Sea and ask itself whether it is building things that will last or simply building things fast enough to need replacing. There is still a harbor wall on the floor of the Mediterranean Sea. It is still hardening. The mineral crystals growing inside it do not know that the cement industry produces 4 billion tons of material every year. They do not know about building codes or insurance categories or supply chain logistics. They're doing what Roman volcanic ash concrete has always done, getting stronger, quietly, without a factory, without a kiln, without releasing a single molecule of carbon dioxide. The Romans did not invent this process. They borrowed it from the volcano. The volcano borrowed it from geological time. The question the construction industry is currently trying to avoid answering is simple. How much longer can we afford to ignore what the seafloor already knows? If you work in civil engineering, materials science, architecture, or if you simply live in a building, look up Marie Jackson and the University of California Roman Concrete Research. Look up the harbor at Caesarea Maritima. Look up what tobermorite is and why its presence in a 2,000-year-old structure changes every assumption the modern construction industry makes about what concrete is supposed to do. This knowledge exists. It is published. It is peer-reviewed. It is sitting in open-access journals waiting to be read. That is how this changes, not from the top down, from the people who know, outward.